So Hodgkin and Huxley were not satisfied by just drawing a circuit. They want to even further pinpoint exactly what is the mechanism, what could be the mechanism in the membrane that enables these two currents and this difference in kinetics of the sodium versus the potassium. So what they did really can be shown here. First of all, we have to note that they recorded currents, potassium and sodium currents, as I showed you before. They recorded the currents, but we could also estimate the conductances, the membrane conductances underlying these currents. Why? Because remember that we already spoke that any ionic current is actually, according to Ohm's law, is the multiplication of the conductance and what we call the driving force for this current. So it's the membrane voltage minus the battery of this particular ion multiplied by the conductance of this ion that gives rise to this current. This is true for potassium. This is true for sodium. The only difference, of course, is the conductance of the sodium channels, and this is the battery or the driving force for the sodium. So this holds true for any current. And remember that in the case of voltage clamp, we fix Vm. We don't allow Vm to change. So if I know Vm, if I fix the voltage, the voltage clamp to a given value, and if I know the battery, which depends on the concentration difference between the outside and the inside of sodium, or between the outside and the inside of the potassium, if I know the voltage clamp value, and if I know the battery of this particular ion, and I know the current that I measure, I can then extract the conductance. So this is exactly what Hodgkin and Huxley did. They voltage clamp the membrane to different values. So here is small depolarization, but still suprathreshold. A stronger depolarization, voltage clamping the membrane step by step. So jumping the voltage from here to here to here to here, and measuring the conductance of both the potassium here and of the sodium for the different voltages. So let's look, for example, at the potassium, the conductance of the potassium. You can see that the conductance of the potassium becomes stronger and stronger as you depolarize more and more the membrane. So the larger the voltage clamp, the more conductance opening of a conductance, voltage-dependent conductance. So I can call it voltage-dependent conductance because when I change the voltage clamp, I get more and more conductance. You can see that the potassium conductance responds slowly to the abrupt change in the voltage. So I change the voltage fast, step. It's a step voltage clamp, and it takes time, as we saw before, for the opening of the potassium conductance. It takes time. And by the way, this time becomes faster as you voltage clamp more stronger. So you can see that it grows faster and also to a more higher conductance as you depolarize more and more with voltage clamp. And when you stop the voltage clamp, you can see the attenuation of the potassium conductance, to its resting value. So I can say again, this is a voltage-dependent conductance. These are ion channels that are sensitive to voltage. In this case, these channels open slowly. It takes them time to respond. When they respond, they are open to a given value, and this given value, the amount of conductance, the degree of conductance change, depends on how big depolarization you have. You have big depolarization, you have big conductance change for the potassium. You have small depolarization, you have smaller conductance. And all these conductance take time to develop. So this is the later current. This is the later outward current that we saw, which does not inactivate during the voltage clamp. But if we look now at the sodium conductance, and you see now the conductance, you are used to look at the current, which is an inward current, I showed you before, but now we look at conductance. So this is the reverse direction of the current. So the current is inward, but the conductance, of course, is not inward. Conductance is always positive. So this is the conductance of the sodium as a function of this voltage clamp. So again, like here, we voltage clamp to this value, to this value, to this value, to this value, and Hodgkin-Huxley recorded the conductance of the sodium for this value, for this value, for this value of depolarization. And here again you see something interesting. First again, you see that this sodium conductance responds fast. So as soon as you have voltage clamp, very early on you get a conductance change, very early on. This is why we call it fast conductance change. This is a slow conductance change for the potassium. This is fast conductance change for the sodium. Fast conductance change. And again, like here, when the depolarization is more and more extreme, you get more and more conductance. You get more and more conductance. So the conductance becomes stronger or larger with depolarization. From minus 40 millivolts to minus 20 to 0 to even plus 20, you get more and more sodium conductance. This is in the beginning. But still, you continue to voltage clamp and the conductance fades away. Somehow it inactivates and it disappears during the voltage clamp. So this is again this conductance that is early, which enables very early on to carry sodium current inside the cell early on, but after some times this conductance turns off and there is no sodium current anymore, although you continue to voltage clamp. This is not the case for the potassium that continues to be open as long as you voltage clamp the cell to a given depolarization. So these are the different two conductances that underlying the voltage sensitivity of the membrane of the axon. So I'm summarizing here. The slow potassium current or potassium conductance does not inactivate during voltage clamp. Note that the K conductance rises slower than it attenuates. And this was important for Hodgkin-Huxley later on to write down the appropriate equation to describe these curves. So it's a slowing growing curve and faster attenuating curve at the end of the voltage clamp. And you see this sodium current, this early sodium current or conductance inactivates during voltage clamp. It's early, so this is the first current that flows when there is voltage change. It's a sodium current, but this sodium current, early sodium current, inactivates during voltage clamp, unlike the potassium current. And here is an example, a direct example of Hodgkin-Huxley trying to fit equations. We shall talk soon about equations. I'm just showing you now a result of an experiment. So this is an experiment of Hodgkin-Huxley recording the potassium current. You see this continuous curve. This is a recording from Hodgkin-Huxley, and the dots here are numerical or mathematical fitting that we shall talk soon about the mathematics, the fitting of the mathematics to this current. You see again that this potassium current grows slowly and attenuates faster at the end of the voltage clamp. So there is a voltage clamp here somewhere, and this is the response. So you can see already now, without talking about the equation, that they somehow realized how to write an equation that the dots, will fit very well the actual recorded current. Actually, Hodgkin-Huxley realized that the fact that it grows slower, the potassium current grows slower and attenuates faster, they realized that they can fit the upstroke of the potassium current or conductance and the downstroke, the decay of the potassium current. They can mathematically write the upstroke as a function that looks like 1 minus exponent to the power of 4. And this means, minus t here, this means that the growth, as you increase the exponent, the growth here would be slower. So if it would be to the power of 1, it would be faster. And if it would be to the power of 6, it would be even slower. Yes, because this is the minus t here. So they realized that they can fit very well this rising phase by this kind of 1 minus exponent to the power of 4, and they could fit very well the decay with a single exponent. And then they wrote this equation. This was a big conceptual jump. They said that the potassium conductance in the membrane behaves like a maximal conductance. So you may think about this like the total, absolute total number of channels, potassium channels, available in this patch of membrane. This is what they call the maximal conductance. This is GK bar. So this is all the available conductance. But not always all this conductance is open, because it is multiplied, the actual conductance is multiplied by a factor that they called N. It's an activating parameter. It is a voltage-dependent parameter, this N. This N goes between 0 and 1. So when N is 0, there is no potassium conductance. When N is equal 1, the conductance of the potassium is maximal, because N to the power of 1 to the power of 4 is 1. So if N is 1, you get all the conductance available of these potassium channels. And if N is between 0 to 1, you get less. The claim was that for a particular voltage clamp, N gets the value somewhere between 0 to 1. At zero voltage, without any voltage clamp, N is very close to 0. At a very, very big voltage clamp, N is becoming close to 1. And this to the power of 4 is exactly what makes things fit this growth. As I said, it looks like this to the power of 4. So this is the basic equation for the potassium conductance. But of course, we have to discuss what is this parameter, which is really the parameter that makes the current both voltage dependent but also time dependent. So N is between 0 and 1, but N depends on both voltage and time. So N represents the proportion of K ion channels in the open state. You can say that if N is equal 0.5, 0.5 multiplied to the power of 4 is the proportion. It's actually not N, but N to the power of 4 that represents how much of the conductance is available. If N equal 1, all the conductance is available. So N is this special parameter, the activating N parameter for the voltage for the Hodgkin-Huxley equations. So Hodgkin-Huxley wrote, these equations may be given a physical basis if we assume that the potassium ions can only cross the membrane when 4 similar particles occupy a certain region of the membrane. So this is another jump. they are now trying to interpret biophysically, almost anatomically, what is this 4 means. They want to say that this power of 4 means that this channel, this potassium channel, that this potassium channel is open only if 4 particles, if 4 gates in the channels are open, so that the channel enables the flow of the current through the channel. So they are trying to give now an interpretation to the number 4, to the exponent 4 here, to this 4, using a biophysical intuition, which we are going to talk about in a second. Okay, and maybe before we go to talk in a second, I just want to complete just showing you another graph from Hodgkin-Huxley about the potassium. This is now really another success of the Hodgkin-Huxley. Just to show you, this is the potassium conductance for various voltage clamp. You can see what we discussed before, that as you increase the voltage clamp, you get more and more and more potassium current or potassium conductance, and that this conductance does not inactivate. It continues at its maximal. It takes time to reach the maximal, but when it gets to the maximal, it stays there, so it does not inactivate. And you can see, by the way, again, that this activation is not only voltage dependent, because with voltage you get more and more activation, so N becomes more and more close to 1. It's not only activated more and more, but also it becomes faster and faster and faster activated. So the activation N, the activation variable N, is both increases with voltage towards 1, and also this activation variable N becomes faster with depolarization, faster and faster, or slower and slower for lower voltages.